So today we will discuss how airplanes fly. This is a first introductory but very practical class with 4 key insights regarding how airplanes fly. During the progression of this course, you will deepen the understanding of this phenomenon, and to be honest, you will master the foundation of airplane flight. By the end of this video, you'll have a good understanding of how airplanes fly. Let's get into the fundamental question we have all asked ourselves at some moment. How do airplanes fly? The first key point to understand is that airplanes have very light structures. This is essential for flight because the lighter the structure, the less lift it is required to keep the aircraft flying. Most of the airplane structure is empty, which minimizes weight while maintaining the necessary strength and rigidity. For example, this Vans RV14, shown in this image, weighs only 590 kilograms or 1,320 pounds. This low weight is achieved by using materials that are both strong but lightweight and by designing the airframe to maximize structural efficiency. If you focus on the image, you will see just how minimal the structure is. Compare this to a Tesla Model 3, which weighs around 3,900 pounds or 1,800 kilograms, or a Ford F-150, which typically weighs around 5,000 pounds. Now, this is a key aspect of how airplanes can fly, simply because they weigh less than one might expect. Even some weigh less than cars. The same logic applies to larger aircraft too. The RV14 weight can be as much as 930 kilograms or 2,000 pounds. So, understanding light structures is critical when designing aircraft, as it directly impacts their ability to achieve and sustain flight. This principle is, of course, fundamental in any endeavor you take in aeronautical engineering. The second fundamental point to understand how airplanes fly is airfoils, which are a clever way to generate lift. The airfoil design has evolved from very rudimentary shapes in the beginning of aviation to sophisticated, optimized shapes in the latter years. Essentially, an airfoil of a wing is its cross-section and is designed to efficiently generate lift as the airplane moves forward. When the air flows over the airfoil's curved upper surface causes the air to accelerate and reduce pressure. Simultaneously, the flatter lower surface slows down the air, increasing pressure. This pressure difference between the upper and lower surfaces of the airfoil generates lift, making the aircraft fly. Additionally, airfoils are designed to maximize lift and minimize drag. By optimizing this shape, airfoils effectively balance lift and drag to ensure stable and efficient flight. So airfoils are without a doubt a fundamental component in aircraft design and why airplanes fly. We will discuss each one of these topics in further depth so that you can understand fully how they work during the course. Take this only as an introduction to the topics. Let us now discuss a third reason why airplanes fly. I personally think this is an underrated reason and is less known in general. So, lift increases with the velocity squared. This means that as the speed of an airplane doubles, the lift force is 4 times higher. Let's say we have an airplane moving at 100 miles per hour. The lift generated could be 2,000 pounds, which we consider as 1x. When the speed increases to 200 miles per hour, doubling the speed, the lift becomes 8,000 pounds, which is 4 times that of previously. At 400 miles per hour, the lift reaches 32,000 pounds, or 16 times the lift we had at 100 miles per hour. This means that by increasing speed, we dramatically increase the lift force generated by the airplane. The same happens with drag, and you can test it out yourself to get more of an intuition. Say that you are driving and you put your hand outside of the window. If you are driving at 30 miles per hour, you will notice the air, but it won't be making much force on your hand. If you accelerate to 60 miles per hour and you put your hand out again, you will for sure notice how the air is pulling your hand back 4 times as much as if you were at 30 miles per hour. So now imagine that you were to drive at 120 miles per hour. In that case, the force would be 16 times that which you experienced at 30 miles per hour. Now, I do not recommend driving at 120 miles per hour, but you get the point. So airplanes fly at speeds much higher than cars, so the lift force is very strong. This, combined with the fact that they are lightweight, makes it easier to intuitively understand why they can fly. The fourth topic is, of course, the engines of the airplane. Engines produce massive thrust, which is the force that propels the airplane forward. This thrust is essential for overcoming drag and allowing the aircraft to gain speed so that it can take off. Engines are made from strong, lightweight materials. The materials must withstand high stress and extreme temperatures, especially in the combustion chamber and turbines areas. So we have to carefully select the right materials for the engines. The challenges related to engines are a whole subject on their own, and we will dedicate a whole module on engines in this course to get a full grasp of how they work and their challenges. In conclusion, airplanes achieve flight through their lightweight structures, advanced airfoil designs and geometry, high speeds which equal to high lift capabilities, and high thrust, powerful engines which accelerate the aircraft at very high speeds. In the next class, we will introduce the two main types of engines that have been employed in the history of aircraft.